Hi folks, thanks for watching. Today we're going to be talking about wave behavior. We're going to be talking about what happens when two waves that are traveling along, maybe these are water waves or some other kind of wave, what happens when they meet one another? Do they bounce off of one another? Do they pass through one another? Do they combine into something bigger or smaller? Do they destroy each other? That's what we're talking about when we talk about something called constructive and destructive interference. The main idea here is that word interference. So I want you to keep that in mind. We're going to look at the following questions. What is constructive and destructive interference? What are nodal points? What happens when waves, after waves interfere? And then this part, this stuff you're probably going to find pretty easy and maybe not too interesting. Where it gets really interesting is when we talk about some of the applications of wave interference. So if you can hang on till we get to this part, I think it's well worth your attention. All right, so let's get started. I'd like you to imagine that you're sitting at the beach, for example, and you're watching the waves go by, and there's all sorts of different kind of waves. You know, there's tall waves and small waves. There's waves that are very spaced out, and some are very close together. If you think back to some of the wave characteristics that we talked about, things like how tall the wave is, how high up it goes, or how low down it goes, that's amplitude. And of course, if we talk about how far apart are the crests, then we're talking about wavelength. Well, to keep things as simple as possible, I'd like you to consider two waves of the same wavelength. We're not going to worry about the wavelength right now. What I'd like you to do is imagine two waves of differing amplitudes that are coming toward one another. So maybe like this wave here. Imagine if this wave was moving to the right, and imagine if this wave was moving to the left. The question that we're looking at is what's going to happen when they meet? So let's take these two waves and draw them just in isolation so we don't get confused with all the other waves. So the first wave is really tall, and it's moving to the right. And just for argument's sake, let's imagine that it rises to an amplitude of, I don't know, let's say 3.0 meters above the equilibrium position. So that's going to be its amplitude. And now let's suppose that another wave, this little guy here, the one that's moving to the left, is of much smaller amplitude. So as it moves to the left, let's give it a 1.0 meter amplitude. Okay, obviously I haven't drawn this to scale, but I'm sure you'll forgive me. So, question, what happens when these two waves meet? That's what we want to answer. Well, we could guess about what happens, or I could just tell you what happens, but that wouldn't be very satisfying. It's always helpful in science to see some evidence. So let's turn to YouTube, where someone has been good enough to post some of the answers to our questions. And of course, I had these videos set up for you just a moment ago. There they are. Okay, so let's take a look, first of all, at this video here. It looks like a classroom setting. You see two students on the ground here, and what they're holding between them is actually a very thin slinky. Maybe at this point in the course we've used these already. If not, we're going to very soon. But also notice that on the ground are pieces of tape, which are spaced at equal intervals. We're going to use these pieces of tape in order to judge the amplitude of the waves that are about to be created. Now this student here is going to create a wave that's going to move to the right. And this student here is going to create a wave that's going to move to the left. And what I want you to do is watch as they approach one another, what's happening to them, and then watch when they do actually meet each other, what happens to them, and then watch for what happens afterwards. All right? So let's just watch what's happening, and I won't say anything. Then I'll play it again, and we'll break the video down into parts, and I'll make some comments. Ready? Here we go. Okay, that's about far enough for what we need. So let's go back to the beginning and now let's look at it in parts. So first off, look at how each student creates his or her own wave. Here's one of the waves. This wave looks like it's 2 tape markers high, maybe 2 feet high. And this wave here is 1.5, maybe 1.5 feet high. And they're moving toward one another. So if you think back to what we drew here, that's kind of like these two waves moving toward one another. Now back to the video, we'll play a little bit more. What happens when they meet? First of all, there's now only one wave. And it's also 1, 2, 3, and maybe even more than 3 tape markers high. So the two waves seem to have combined. And if you guessed that the original wave, which was about 2, and the original wave here that was about 1.5, 2 plus 1.5 equals 3.5, which is roughly what we're dealing with here. If you guessed that the waves just add up, then you're absolutely correct. So going back here, what happens? Well, this gives you a taller wave where you just add up the 3.0 meters plus the 1.0 meters to get 4.0 meters. And that's basically our lesson. The rest is just details. This is what we call the principle of superposition. Superposition means, oops, that was a pretty bad line there, I didn't mean to cross that out. Superposition means to put one thing on top of another, to plop things on top of one another. And the principle of superposition says when two waves meet, they overlap and their amplitudes add. That's it. There's really nothing more to it. What happens after the waves meet? Do they bounce back and go back where they came from? Do they continue going through one another? Let's look at the video for an answer. Remember, the big wave, the taller of the two waves started on the left, and the smaller of the two waves started on the right. Watch what happens after. The smaller wave is now on the left, and the larger wave is now on the right, and they're both about the same as their starting amplitudes. Remember, this guy sent about a 1 or just slightly higher than 1 tape marker high wave. There's the 1. This guy here sent a 2 marker high wave, and there's the 2. So after interference, it's important to note that what you get is now the blue one will be on this side and continue going that way, and the red one will be on this side and continue going that way. So also part of the principle of superposition is that after the interaction, the waves continue on as before. They don't get destroyed, they don't bounce back, they just keep on going. All right? A couple of other things to note. When waves do this kind of thing where two crests, as you see here, add up into a bigger crest, we call this constructive interference. Constructive meaning adding up to more than before. Okay? And if the two crests form a very large crest, you might also hear me use the word super crest to talk about the resulting large crest that's been formed. So there's a few terms for you: superposition, constructive interference, supercrest. All right? Now let's move on and ask ourselves what would happen if the reverse interaction occurred. What if a crest met not another crest, but rather a trough? So I've got another video for you that I'm going to show in a moment. Before I do that, I'm just going to lay the groundwork. Suppose this time our 3-meter tall wave that's moving to the right encounters a crest, a trough that's moving to the left, and this time I'll make it 1.0 meters in amplitude. This one being 3.0 meters in amplitude. Okay, so what's going to happen when these guys meet? Can you guess what's going to happen? Are you guessing that 3 up and 1 down leads to 2 up? Will there be subtraction in this case? Not a bad guess, but evidence is what we have to look at. So let's look at another video that was posted here where this scenario is set up. Ready? Once again, I'll let you watch the video and then I'll comment on it after. Okay, seen enough there to answer the question. If you watch in the beginning, the waves that are coming toward one another, okay, let's pause here. You see a crest over here going to our left. Here you see a trough going to our right. Let's let the video run and look what happens when they meet. There is, in fact, some sort of cancellation or subtraction going on. In this case, the cancellation is total. Why is it complete? Well, the two waves in the beginning, if you look, they have about the same amplitude as one another. And so when they meet, you get 0 as the amplitude. We have a name for that. If you get perfect cancellation, we get what's called a nodal point. Once again, after the interaction, the original crest, which this guy sent the first time, remember he sent a crest over here. Whoops, sorry, let me get out of full screen mode. This guy sent a crest moving to the left, and if I go back a little bit, there is the crest afterwards that has passed through. And this guy over here sent a trough that was moving to the right. There's the trough. So once again, the waves do pass through one another. After the interaction, they're unaffected. But during the interaction, if a crest meets a trough, they subtract. So if you guessed, there'll be some sort of smaller wave, 2.0 meters in this case, you were correct. 3.0 meters plus we're adding a negative 1.0 meters does give you 2.0 meters. This is still superposition, but we actually call this destructive interference. And of course, if you have a situation where a, let's say, 3-meter trough, or crest rather, were to meet a 3-meter trough, what would happen here? You'd actually end up with total cancellation, and we call that a nodal point. All right, so let's just look at where we're at here. What is constructive and destructive interference? We've answered it. What are nodal points? We've answered that. What happens after waves interfere? They continue on as before, and that's the end of it. So at this point, we've pretty much covered everything we need to in terms of the basic learning in this video. What I'd then like to do at this point is get into some applications, and I'm really only going to talk about one application in some detail. The rest, I hope you'll get excited enough about the first application that you'll want to go and learn more about the others. But this first application that I'm going to talk about deals with something I'm sure you've all heard of, and that is a gentleman by the name of Einstein. Everyone's heard of Albert Einstein. He's that physicist who developed the special theory of relativity. And what is the special theory of relativity? Maybe you know a little bit about it, maybe you don't, but I know that you all know this equation. It's the most famous equation in the world, E equals mc squared. The E stands for energy, the m stands for mass, and the c stands for the speed of a wave that we are all familiar with. That wave is light, the speed of light, and you're supposed to square it. By the way, just for your information, what is the speed of light? It is 300,000 kilometers per second. Exclamation mark. That's pretty fast. That would get you from here to the moon in just over a second. That is very, very fast. If you could travel this fast around the equator of Earth, you would circle Earth more than 7 times every second. That's how fast you'd be going. So the speed of light, a wave, is in fact very fast. But I digress. Let's get back to what I was talking about. How is this related to interference? Well, Albert Einstein's famous special theory of relativity, from which this equation comes, is based on the idea that the speed of light is constant for every person observing light in the universe. Now, this may not seem like a big deal to you, but to know that there's something in the universe that everyone can agree upon, that's a pretty rare thing. There are not too many things in life where everybody agrees on what's going on. Well, in physics anyway, there are a number of things, and one of them is the speed of light. We can all agree, as you're going to learn in the grade 12 course, so by the way, make sure you sign up for the grade 12 course, we're going to learn in grade 12 that the speed of light is the same no matter what for all observers. Now, that forms the basis of the special theory of relativity, which is a hugely important theory. It has applications in nuclear physics, in astronomy, you name it, it's got applications. GPS, global positioning systems, satellites, which relate to telecommunications and your cell phones and GPS tracking and all that, hugely important. What's it got to do with interference and light? Well, I'd like you to take a look at a diagram that I took from Wikipedia in an article called Wave Interference, or rather, probably took it from an article called Interferometry. What is an interferometer? Well, first of all, in the word interferometer, you see the root word for interference. This is a machine or a device that is based on the idea that when light waves interfere with one another, you can learn something about the light or the thing that's doing or creating the interference. Now let me show you what I mean. You start off with a light source, perhaps a laser. So imagine that here's a laser beam, a red laser beam moving to the right. Now in this device, it hits what's called a half-silvered mirror. What's a half-silvered mirror? Imagine you're looking at a mirror that creates a good reflection of you, but also you can see through it. So, you know, if you ever look in a car window on a sunny day, you get a reflection of yourself, but you can also see through. The same principle is applied here with the half-silvered mirror. So what does this half-silvered mirror do? Well, first of all, it takes some of the light that's hitting it, and it bounces it, it reflects it away. So I've drawn a blue line here to show that. Okay? And it also lets some of the light just go through. So I'm going to use a green line to show that. Some of the light continues on its way through. Okay, there's green right there. All right, now, at the end is another mirror. This is a full mirror, so it just bounces the light back. And there's another one here, which bounces the light back. So let's show that this light comes back this way. And we'll show a little arrow there. And we'll show that this light here is bounced back by the mirror. So far, so good. Nothing too crazy going on here. But now look what happens. This blue beam, because it hits the half-silvered mirror again, some of it can go right through. And it does. So I'm going to put some blue in here. But the same thing is also happening with the green light that originally went through the mirror, the half-silvered mirror, and bounced back. Now some of it's going to bounce this way. So in green, I'm going to show you alongside the blue a little bit of green. So in here, you've got the green and the blue beam recombining. In other words, you're back to the same parts that you started with. In other words, there are two waves that have rejoined. Well, isn't that what we just finished discussing? Two waves meeting. They can have constructive interference, forming supercrests, or they can have destructive interference. Maybe they'll form nodal points. Something's going to happen. Well, what scientists do is they study the light here. Whoops. They study the light here in a detector. The detector could be anything that detects light. It could be a microscope as an example. It could be something more exotic than that. But the point is, they look at how the light rejoins. And they see things like constructive interference. Now, can you guess what would happen if two light beams joined up and interfered with one another constructively? I'll give you a moment to think about it. If two light beams joined up and interfered constructively, what would that look like? Pause the video if you have to. Okay, I'll assume you've unpaused it now and thought about it. If two light beams overlapped, if they superimposed and interfered constructively, you'd get a brighter than normal light beam. And of course, the opposite is true if you have light beams joining up and interfering destructively, then you get a darker beam of light. And so what you end up getting, let me just go to Google here, and I'm going to do an image search under light interference, and we'll see what that brings up. And now what I'm looking for, here's an example. Actually, this is more what I'm looking for. What you'd end up with, look down here, is alternating bright and dark areas. Here we go. Bright, dark, bright, dark, bright, dark. Constructive interference, destructive interference, constructive interference, destructive interference, and so on. Now, you'll learn more about this in the grade 12 course. However, the point is, sorry, as I just get back here, the point is that in doing this, the interference tells you about what happened to the light when it was broken up into two parts. And how did we get started on this in the first place? My goodness, we're way off on a tangent, aren't we? Well, no, not exactly. Albert Einstein, whose special theory of relativity is based on understanding light, he was able to come up with this because two other physicists did an experiment where they used the interferometer to show that the speed of light is constant for all observers. And that forms the basis of the special theory of relativity. So if you think the special theory of relativity is cool, and I'm sure once you learn about it you will think it is, then you might as well also read a little bit about Michelson and Morley, two physicists who did the experiment that helped Einstein develop his ideas. All right, that's it for today's video. As you can see, the mathematics is pretty easy, it's pretty straightforward. I'm going to leave you with one final video, and this video is something I guess you shouldn't try at home. Well, you won't be trying it at home because there's no ocean near your home. However, it's called bodyboarding backwash, and here's a bunch of surfers or bodyboarders in the ocean enjoying wave superposition. See if you can figure out what's going on here, folks. Thanks for watching. I'll see you next time. Enjoy the video.